a wheel of mass 2.1 kilograms and a radius r, okay, rests on a horizontal surface against a vertical step of height h. A point below the center of the wheel is a distance x from the vertical step, okay? The wheel is to be raised over the step by horizontal force F, okay? Applied to the axle of the wheel as shown in the figure. The angle between the horizontal force and the line connecting the center of the wheel and the point of contact of the step is phi, which is 65 degrees. Okay, so we know this is 65 degrees. And we know the mass of the wheel is 2.1 kilograms. We don't know r, that's a mystery number, but it might be that all that matters is that the relation between r and h and x. And that relationship is given to us by this angle, phi. Okay, which expression gives, I'm going to clean this picture up, that way I can draw on it some more. Which expression gives the magnitude of the torque that gravity exerts on the wheel about the point of contact between the wheel and the step. Okay, so torque equals r cross f, where these are all vectors. And this implies that torque, without the vector, equals the radius that is perpendicular to f. Now I know this f in this case is going to be due to gravity, so I'm going to draw that in right here. This will be force due to gravity, and this will be r. Let's see, which expression magnitude of the torque that gravity exerts on the wheel about the point of contact between the wheel and the step. So we're like wheel, step right here. This is the radius r, and so when we're looking for the perpendicular, because we can decompose this r into two parts, so we'll do it this part here, that part there. So we have, yep, kind of like so. And from this point, we can look at this and we want to find out the torque. So this will be r, I'm going to call this r perpendicular. So that's the one we want. So there's two ways to look at this. This magnitude is also r fg times sine of theta, where theta is the angle between the two vectors, but sometimes that can be kind of confusing because then you have to figure out, all right, is it this phi right here, or do I have to do 90 minus that? And it gets confusing. So in this case, it actually, I think, probably be this angle, which would be the theta. But I'm not going to worry about that because I'm going to look at it as the perpendicular component of the radius times force. So if we look at this r perpendicular equals, it's going to be the cosine. So it's going to be r cosine of phi. Because SOHCAHTOA, I know, you guys probably totally understand this. You don't need me to go over the trig. So cosine is adjacent over hypotenuse. So it's going to be this one. The way you're going to get the adjacent is going to be r cosine theta. Okay. And so then the torque between the wheel and the step will be r cosine phi times force gravity. Force gravity will be mass times gravity. Will be mass times gravity, which we know what the, do we need an actual answer? No. We know what the mass is. We don't know what we do know what the mass is. We do know the gravity. We don't know r though. That's the question here. Okay, so r cosine phi, mass times gravity. R cosine phi, mass times gravity, right there. So C will be the answer for the first part. Second part, what is the minimum horizontal force needed to raise the wheel above the step? Okay, so when you see something like minimum force needed, what you should really think of is 0. So we have a force gravity pulling it down, and so we have torque this direction due to gravity, but then we're going to have a torque that direction due to big F, this big force. And when torque big F is bigger than torque due to gravity, then the wheel will move. The wheel is not moving right now, okay, with torque F being small, because it's basically resting on the ground. The ground is providing some normal force. But as we're pushing, this force is getting bigger, this normal force that's pushing, holding up the wheel is diminishing. Eventually that will reach 0, and then the torque will become unbalanced, and it will rotate over the wheel. So when torque force is small, you can actually think that there's a torque normal from the ground pushing up. That as the force gets bigger, the torque to the force gets smaller, and that's basically taking out for this torque normal as that's getting smaller. A little bit more background information than you probably need or desire. Okay, so what we want to say then is we'll look at this part right here, torque force, torque gravity. So I'm going to say torque gravity equals torque force. We already know what torque gravity is because we just found that out. It's mg r cosine of phi. And then torque force is going to be, I'm going to erase this, zing, so I can look at it a little bit more clear, so I can redraw things. So we have torque to the force will be r cross f, just like it always is. I'm going to call this r perpendicular, so this radius and the cross product, I'll combine these two together to call it r perpendicular times the force. And so in this case, force is going this way. So we have we'll call this Rx, we'll call this Ry. Well, in this case, Ry will be the R perpendicular because the force is in the x direction, A perpendicular to the x direction is the y direction. And when you're talking about two dimensions, there's only one answer. We're going to ignore z for now. This Ry will be the R perpendicular. So we have this, which we can then, using the SOHCAHTOA, this will be R sine theta. So we have, I'll do big R, sorry. Big R sine theta times force F. This is asking what's the minimum force? What's the minimum horizontal force? F. So this is what we're looking for. And so we can write this down here, or I can be more efficient and copy paste. Copy, paste, adjust, remove extraneous underline or excessive underline or extra underline. The r's cancel, which is convenient because we don't know what it is. And we have that F equals mass times gravity times 1 over, and this is cosine over sine, this is supposed to be phi, not theta, over tangent of phi. So, yes, because sine over cosine is tangent of theta, so cosine over sine would be cotangent, but it's harder to do that on my calculator, so I will call it 1 over tangent. 2.1, so we have 2.1 times 9.8 divided by the tangent of, I think phi is 65 degrees right here. Whoop, 65. So this really isn't a difficult problem, but this is the first time you've seen it. It's, a little confusing, and you really don't know what's going on. That's also a reason, by the way, this inherent confusion of this kind of problem is why I like to think of things are less in terms of trying to do cross product by using the sine of theta, the traditional magnitude of a cross product of sine theta. I like to think of it as r perpendicular. That way you get slightly less confused with which angle you're talking about. Whoops, I can quit. All right, so we're in degrees, so we do 2.1 times 9.8. I could do 9.81, but 9.8 is good enough. Divided by tangent of quantity 65, close parentheses, and I got 9.6. 9.6, and this will be measured in newtons. Okay, look at it. We got here. Bam, even a possible answer. How fortuitous. Okay, So backtrack real quick. What we did here. So we're given all this data about this wheel rolling into a step. A relatively small step, relatively large wheel. Drawn reasonably close to scale. And first thing we want to do is find out the torque that gravity is working on this wheel here. And normally we wouldn't think of it in terms of a torque of something, of the wheel just sitting there, but you absolutely can. So there's torque equals R cross F, arrows. And so we have a torque. Now, torque is actually, the correct way of drawing torque would be the Z and, I guess in this case, into and out of the page. Because when you do a cross product, the resulting vector is perpendicular to both vectors. But it's more convenient to look at this as clockwise, counterclockwise. So gravity will be doing a counterclockwise torque, but it's resting on the ground here, so there's going to be force up, and there's going to be another component, probably like that, of another perpendicular, and so we're going to have some sort of normal torque that's basically holding it up. And this normal torque is basically preventing the ball from, rolling into the ground. Then we take this force, we're adding a force here. As this is pushing this way, we then have this torque based on this R perpendicular. R cross F again, same idea. And we're creating a clockwise torque. And as that torque is rising, it's basically lifting the wheel off the ground. Normal force is based on how hard it's being pressed against the ground or another surface. So this diminishes, and eventually the force is great enough to create a torque in the clockwise direction that is greater than the torque in the counterclockwise. Therefore, we have motion. So torque, the force equals ma equivalent, is moment of inertia times alpha, where, I guess probably like this, where eventually, once our summation of the torques is non-zero, then we get some sort of angular acceleration, i.e. the rolling ball, or disc, or sphere, or some such, which will help then determine the moment of inertia, because moment of inertia is based on the geometric shape of the rolling object. Okay? Put things together, did some math, solved some problems, and this is what we found. Hope that helped. See you next time.